All right. So before we start, let me nag a little bit about last session. I kind of felt really tired after the last session because I think we didn't really manage to communicate. I think the level of understanding that I wanted to communicate was not really communicated. And that moment at the end was very embarrassing, the no question moment. Shruti was trying to save the moment, but it was kind of a very large silence. So, and that's not a good sign. So I thought a lot about what went wrong last week, and I watched the video again, and I think I have a theory about that. I think it's the artifact of Zoom teaching, and we are both new to this. The problem with Zoom teaching is that I don't see you guys. And like when we are doing a real class, I mean, the definition of real is changing these days, but the old way of doing it, we would be in same space, subject to same temperature, room temperature, everything would be the same, and we see each other. So I can see your eyes, I can see when you don't get something and I have to explain more, and I can see like when I am explaining something too many times. Now it feels to me like driving with my windshield covered with mud. Basically, I'm driving blind. And the video of the last session was quite desperate. I found myself like repeating same things five times, and that was like a stupid thing that it really didn't need that much explanation. And for other cases, I didn't know how deep should I go. So so I thought before we start the class today, because this is a practice that we are doing together, and we want to sort of make good use of our time. Let's change a strategy a little bit. So I will be interrupting you more in the middle of the conversation. We initially wanted to have some poll setting, but it seems that my account has some problems. So, but first I will stop more. Second, I humbly ask you guys, every one of you, if you don't understand something, jump in and ask. That's why we have our numbers limited, and so we can talk. Otherwise, if it was like a one-way thing, you could have listened to a recording. So the idea is that we are doing it together. So every time, there is no such thing as a stupid question. And honestly, the selfish part of this course for me is your questions. Because when you ask a question, the question comes from a new point of view, new perspective, and it sort of makes me more aware of what I am talking about. So your questions are the learning experience for me, basically. So I want to ask you guys to help with this situation, because we are not in same space, and at the end of the day, we want to make use of this time. If the concepts are not communicated, what's the point of doing this? So feel free to interrupt me. Any point that was not communicated, just ask a question and go to the bottom of it. Remember, one philosophy that I have for this course is that I have a feeling that something is changing in education, in a sense that we are outsourcing stuff now more. We have computers, we can outsource mental functions now. It's like, okay, let's look at the stats book. They say I should do a DPrime here. Look up what is the DPrime formula. Let's put it in my code and get a DPrime. And without understanding it. And of course, we can survive that way, but who is going to understand things? You are the scientists, so you are the ones in charge of understanding, deep understanding, and making use of those concepts. So there is no one after you. You cannot outsource that to anyone else. You have to have a deep grasp of those concepts. And I understand that math can be annoying sometimes, so I kind of try to remove as many formula as possible. But the basic math concepts are your job, as our jobs. Basically, we should be on top of them. And when we grasp them, when we treat them as something that has to be completely visualized and understood, after and only after that, you will feel confident about your science. You will feel like you know what you are doing, and you will have this sense of independence in your thinking. So that is our goal, and I wanted to ask everybody to help achieve that together. So now let's move on to our story, which is signal detection theory for today. Uh, what are those guys doing? Anybody has any idea?
Are they spies listening in on conversations?
Good call. But they are not spies. They are radars. They are they are the old. They are airplane spotters. In the First World War, they had these funny things in their ears, so they can actually hear the airplanes. And they have pinhole cameras, so they can spot the airplane in the bright sky, and basically point to the airplane, like that's where the airplane is coming from, and then they could do something about that. Well, there are more serious examples of this tool that's sort of for seeing farther away. There are all sort of, if you look at that period, there are all sort of interesting inventions. This one is inspired by owl ears, have some vertical disparity to spot the position better. And this is like a handsome variable model with metal finish. And this is more of an industrial example. So this was the mode of detecting signals, basically, in up to Second World War, basically. And our story starts from here, and surprisingly, carrot has an honorary appearance in our program, very short. So this is where I wanted to do a poll. So I come out of the presentation mode, and we do a poll here. So I want you to raise your hands if you think that carrots are good for eyes. And specifically, I mean sharp vision and night vision. So let me see, how can I see everybody now? All right, do it. Let's do it. Half, something like half. Yep. All right. Okay. So let's say half of us, right? Yeah, that was my impression. Okay. So let's go back to the presentation. So how come carrots became so good for eyes? This guy who got like Medal of Honor from the Royal Air Force, British Royal Air Force, is named John Cat's Eye Cunningham. And John Cat's Eyes was this pilot who made lots of actually managed to shoot down many German airplanes during the war, and he got lots of medals. And the secret to his success was eating lots of carrots. And it actually led to some sort of educational pamphlets coming out that about like night sight. If you want to have good night sight, eat carrots because they have vitamin A and all that. But the reality was that the whole story was a campaign by MI6, by the British intelligence system, to hide the fact that they had invented radar. So this was a PR campaign for the Germans, aimed at the Germans, so that they don't, because now the British were hitting lots of German airplanes, and they were like, okay, Germans are gonna wonder how come we are hitting their airplanes that much, and let's give them carrots instead. That was the idea. And it is quite funny that the idea has stuck even though the war is over, even though the Germans actually acquired radar like a little later down in the war. So radar was invented, and now we had some sort of mathematics of signal detection. We could think about signal detection more rigorously, more seriously. And signal detection theory actually came out of radar. That's when you want to detect a signal which is near threshold. And how do you do that? And how are you subject to errors when you do that? How do you analyze the data related to that and stuff like that? So okay, this is where I was hoping to have like some numerical polls, but let's say now I'm going to flash a dot on this noise and wanted to see how many people saw it. Is there anyone who has the sort of general view to give me a sense of how many people saw it? Because I don't see you guys now. I see only 5 people.
Arash, if everyone wants to just use the hand raise function in the participants window, then we'll be able to see. So if everyone just
okay,
raise their hand when if they see it on the participants window.
All right. So ready? 1, 2. There will be like for 200 milliseconds, maybe a flash or nothing. 1, 2, 3. How many saw it?
1, 2, 3, 4, 5, 6, 7, 8, 9. It looks like almost everybody. Well, half of everybody.
Half of everybody.
Yeah, half. I think about half.
All right, half of everybody. So now, and remember that the noise changes. You're not looking for a refreshment of noise. You're looking for a bright dot appearing. Well, sometimes not that bright. Now, boom, how many saw it?
A little bit less than last time.
So one thing is that it's appearing after you say it's appearing because of your lag. So yeah, it's coming like a second after you say now to everyone.
I see.
Yeah.
Okay. So just add 1 second to my now, or I will do it. Okay.
Okay, everyone lower your hands.
Yeah. So what is the number, Rosa? Give me a number.
Oh, it was a little less than half that time.
Whatever. Shall we call it 45?
Yeah. I'll count next time.
Yeah. So ready?
Yeah.
Now +1.
I think more than half. That was more than half.
All right. Nice. So now let's move on, because I wanted to do like multiple trials and actually make a psychometric function of our data. We can't do that now, but that doesn't matter. It will be like something like this, although it appears that in this case we've got like those top numbers are pretty low, and that's interesting. So it is kind of like something like, I don't know, maybe let's say 60. Yeah, let's not bother with that. But it will be a function like that. The brighter the dot gets, the more likely it is that you see the flash, right? And we can make a psychometric function that shows that increase. In, well, this case is going to 100 because I expected it to be very easy, but we had so it kind of goes up to probably from 0 to 50, something like that, if we collect that data. But now Now, imagine I run exact same task on you guys, exact same task, but tell you that if you make a mistake in detection, if you false alarm, if there is no dot there, and you say yes, some disaster will happen. There will be a nuclear war, something really major. If I run the test under those conditions, this curve will be shifted extremely to the right. You would be very careful not to jump the gun too fast, right? So you will change your internal criterion. But if I say it's fine if you false alarm, but if you miss, you will be missing something big. You have to actually detect it. You should not miss it under any condition. Then you will change your threshold of like calling it a hit or not, calling it a signal present stimulus or not. So this curve will shift to the left, basically. As you sort of are more now prone to detect yes, to say yes than no. So this creates an issue of choice biases. So in both conditions, let's say we've got the normal condition and the condition that I say, if you say yes, if you detect something that is not there, but you say yes, there will be a nuclear war, and you will change your criterion. In both cases, you see it just as well. You see the stimulus just as well. Your cognitive discriminability for the stimulus is the same. But your outcome will be different. Basically, if I want to reward you based on your percent correct, you will get different numbers. So the concept of a lax observer versus a strict observer is born now. So basically, you can have an observer, or an observer, given observer could be in a lax condition or a strict condition, depending on the cognitive state. Or you could say, this person is a lax observer. That person likes to say yes to everything, easily let the yes comes out, right? The strict observer is more stingy with yeses and doesn't say yes until he or she is really sure that there is some signal. So even though both of these, and remember, we are talking about radar history, so these could be both radar operators, right? And these radar operators, one of them could like say, airplanes are coming all the time, and they fly and see like only 10% of the case he was right. The other guy is not saying airplanes are coming all the time. He only says it when airplanes are coming. But sometimes airplanes come without him saying they are coming. So he actually misses airplanes coming. So how do we deal with that in neuroscience and in psychophysics is the topic of our session today. Basically, what I want to communicate today at the end of this class is to communicate the difference, a deep sense of the difference between performance, which is traditionally shown with percent correct at a task, and discriminability or sensitivity, how sensitive you are to discriminate things from each other. That's what you want to know as a scientist. But performance is the measure that we usually use to show that. I'm using a lot of basically information from this paper. This signal detection theory is very old, and it has a long old literature. I'm not going to go into that. But if you want a good read, I recommend this paper by Harold Stanislaw and Natasha Todorov. It's a very good read, and I'm using a lot of my material from that. I'm borrowing from them. So here is the idea.
Can you please go back to your previous slide really quick so I could take a screenshot?
This one? Sure.
Yes. Thank you.
Thank you for interrupting. I feel alive. So now, probability of occurrence is on our y-axis. Sensory intensity is on our x-axis. What does that mean? Let's say let's say I have noise, a patch of noise, and I am adding some signal to it, right? The noise itself varies. Sometimes it's bright, sometimes it's dark. So if you look at a pooling zone of the size of that spot on the noise, the average intensity of that zone varies. Sometimes it's to the left, it's very dark. Sometimes it can be quite bright. When you add that blob of white on top of that, you are changing this distribution, shifting it to the right. And now you have basically the cases that you're supposed to say yes, because there was actually a sensory stimulus, a flash in there, or the red distribution. They can be darker than the flash, right? Because it can be superimposed on top of a dark patch of noise. So sometimes they can overlap the two distributions of the intensity. And your job is to basically tell apart the red ones from the blue ones. Is it unclear at this point? Anything unclear?
I want to ask as to why there seems like there's like almost some inhibition, like when you are centered like right at the middle. And yeah. Do you
inhibition? What do you mean by
so
inhibition?
The number of, like if you have noise plus signal, you have like right in the middle on the x-axis, you have like a point where like there's a smaller chance of there being an occurrence when there's like an equal, when the opacity is exactly 50%.
Right. Okay. Oh, okay. I see what you're saying. So let me explain. Thanks for speaking up. So if you make a small circle in the middle of the noise and average the intensity of the spots there, you will get a distribution. It is most of the time you will get average gray, right? That's why you get in your blue Gaussian curve, in the blue bell-shaped curve, you see that the center is the highest amount. That's the gray that you get. But sometimes you get a lot of black in there. So that condition is less likely. So the darker the average gets, the less likely it is to have that condition. That's when we are moving to the left on the blue curve. Now we are not adding any stimulus, any flash to this. It's just a noise, right? So now if you average those spots, sometimes by just chance, you get all white accumulated, a patch of white there. That will bring up your average to the numbers that could be comparable to the time that you actually have a sensory stimulus there, right? Yeah. So that's the crossing point, basically.
Okay.
Right, that's the crossing point when your stimulus is falling on top of a bunch of black pixels to bring its intensity lower, or your noise happens to have lots of white spots there that brings the intensity high, and they cross, right? And that is the point that is hard perceptually to discern.
So in one case, you don't actually have a signal, like you don't actually have a spot, but you have enough signal in the noise to think that you have a spot.
Yes, exactly. Cool. So now the question is, what's the solution? I am not the God. I don't know if this stimulus belongs to the red distribution or to the blue distribution. So how do I do this task? I just put a line in there. That's what a cognitive operator would do. I put a line in there and say, that's my line. If the patch is brighter than that line, I will say yes. If the patch is darker than that line, I will say no. So now, if I'm a lax guy, I have a lax, or sometimes they say liberal criterion. I'm fine with saying yes, lots of yes. So I basically bring my criterion down to the point that I'm sure no noise plus signal, no red case will fall below me. Well, sometimes they do, but most of the cases I don't mistakenly say no to them, right? I just say I don't miss them. But if I am a strict person with a strict criterion, I shift my criterion high up there. Only if I see a bright spot and I am confident that's not noise, I would say yes. So my yes is more valuable. But my no's are crap. I am missing lots of actually signal present cases. Clear?
Yes, Arash, it's very clear, but maybe you want to define exactly what you mean by probability of occurrence. What is an occurrence and what probability of an occurrence is. That would make it more transparent, perhaps.
Sure. Thank you. Yeah. So that is basically frequency. That means that out of 100 times that I generate this stimulus, how many times it happens that in that pooling zone that my circle is supposed to show up, what would be the average intensity in that pooling zone? So what happens is that, let's say I make 200 noises and measure, and it find out that for 100 something of them, actually, that pooling zone, if I average it, I'll get a gray, right? That's the peak of the blue curve. That's the probability of occurrence of that gray is high.
So why is the red curve why does it not plateau to the right? Like, why does it have a peak and then come down? If the sensory intensity, is the sensory intensity increasing for both the noise and the signal, or is it just the signal?
Now we are talking. This is good. So the other one is basically the same distribution, which is dictated by the distribution of black and white pixels in our noise. And now we are shifting it just by adding some basic number to it, right? So the whole distribution goes up and then comes back down again. So now basically it means that our average intensity when we have the stimulus is that number, the peak of the red. But higher than that average, how do you achieve that? That's basically a matter of luck. If you get your white patch there and a bunch of white pixels at the same place, then that will bring your average up.
Okay, so
that's unlikely.
Your white spot, it never changes. You always introduce the same white spot, and what's varying is the noise distribution.
Exactly. In this example, that's exactly the case.
Okay.
Yeah.
Wait, it's always the same white spot?
Yeah.
It's always the same like low opacity white spot that is adding to the noise.
Exactly.
Okay.
So if you take our if you take our psychometric curve, this is a cut from that. So we are talking about a cut from middle of the curve, where it is kind of noisy.
Cool.
So the only thing that's varying is the underlying noise, and that's what's causing the white spot to vary in its obviousness.
Exactly.
Just to be sure, so what you're saying is that the spot remains the same at each level of the x-axis, and then you have many instantiations of the noise. Of course, if you go so then and then you get your probability by just looking at the added value of your patch, and you compare that with the noise, and that's how you get your probability.
Exactly.
The probability
that's the y-axis.
And the occurrence would be that you actually did have a patch shown, in the time that you were looking at it. But then, of course, sensory intensity says how strong is the white patch. So from the axis of black to white.
Exactly.
So you get a probability.
If you have a whiter patch, if you add a whiter patch, the two curves will be separated. The red will shift more to the right.
Yeah, that's I think that's very transparent now.
Yeah.
Then, so this would be different than having a high contrast stimulus. This is because now you're saying that sensory intensity is if the noise basically creates that circle, right? Like a bright white spot. It's
correct in this case. Although in the general case, this is sort of the most concrete example. In the more general case, a lot of noise comes from our sensory system, basically. So we want to take that into account too. Basically, even if you show a noiseless stimulus, there could be noise in different levels of visual processing. So that would be the general case. But for this specific case, we are not talking about even contrast. This is basically luminance. That's the criterion here, where we put the criterion.
And the reason the blue curve peaks is because even without a stimulus, even without a white spot, on occasion you will have a cluster of white, and that counts as an occurrence.
Correct.
Okay.
Exactly.
Okay.
Exactly. Is everybody with us?
Yes.
Actually,
Cool.
that last thing that Rosa said, why does it peak like at a low sensory intensity? Oh no, I guess I understand.
Gray, right?
I guess it's just the probability for that. It's like a Gaussian.
Yeah. The low one, that's the middle gray, right? The average gray is a peak, because most probably you will get average gray if you average a bunch of white and black and white dots.
I guess what I don't understand is why average gray counts as an occurrence. Like what is?
Oh.
I thought we were looking for a white spot.
Yeah. So I make one noise, right? Let's say the task is a super simple task. There's a white dot in the center, right? So I make a noise number one, and look at the average intensity in the target area. Most probably it's 128 or 127, the average gray, right? And then I make another noise. It's 128. The other one is 126. The other one is 129. So they're around the average. So most of them are that gray, right? But sometimes I get lucky and or actually unlucky, and I get lots of white spots there, right? So that's when the noise crosses, and the probability is probability of occurrence on a stack of noise.
I get it. Yeah, it's probably of general occurrence, not of perceptual occurrence.
Exactly. Yeah.
Okay.
Yeah.
That was the confusion.
Yeah. So now if you do that, so basically in the previous case, all of us, even if some of us are strict observers, some of us are lax observers, we all see the same thing, perceive the same thing, and we have the same sensitivity, but our criteria is changing. But there are cases that the sensitivity changes actually. Let's say if I do that task for somebody with normal vision, I get that. But now if I have somebody with low vision, now the aberrations of the eye are added to what I have created there. So that blurs the function now. And now the function is less discriminable, because I have just, my sensory apparatus cannot capture it as well. Now the two cases are more mixed up, right? Or if I am John Cat's Eyes Cunningham, and I have really cat's eyes vision, for me, the separation will be more. For me, I am more sensitive to that little blip and increase in intensity, so I can separate the conditions much better. What we want to do today is to separate that. So in this case, the Gaussians are actually more separable. So the sensory system can see the differences better. The challenge of us is that how can I tell the difference between that and the case that my performance varies because I am moving my criterion around? I will explain more. So let's say basically we want to find this measure called DPrime, which is a measure of discriminability independent of your choice bias, independent of if you like to say yes or if you like to say no, if you're stingy with your yeses or you are very generous with your yeses. Independent of that, DPrime is a measure that actually looks at the underlying distributions and tell us how separable they are for this subject. So basically, there are two factors that matter. Factor number one is how far are the two humps of the Gaussians. The farther they are, the easier to discriminate them, right? So that means that we are using a brighter and brighter and brighter stimulus, right? So Simon, back to your question about the psychometric curve, if we take a sample from the top parts of the psychometric curve. When we showed a really bright stimulus, right, the two curves will separate because the average of stimulus plus noise is now more. It's easier to discern. So that's a positive. So when please, yeah.
So in the noise only,
can you say your name, because I'm blind, I don't see you.
Sorry, Malcolm.
Malcolm, hey.
In the noise only, what is changing as sensory intensity increases? Because I get for the signal, the stimulus is getting brighter.
Yeah.
But what's changing per se when it's just noise?
Aha. So basically, when you have noise, the thing that changes is not the average, is the standard deviation, right? Okay. So you could select your noise from, you could have a distribution of noise which is a narrower distribution, or have, right? Or if you are, or if you have low vision, it actually, your eyes will turn it, will widen it for you. You don't have to do anything with the noise, right? And so the wider that is, the worse the D prime is, right? That's the point I want to communicate with this slide, that if your distributions, the distribution that you want to detect and distribution that you want to ignore, if they are farther away from each other, D prime goes up. They are more discriminable. It's quite intuitive. And each of them, if their standard deviation is increasing, D prime goes down. They become less discernible from each other. They overlap more with each other. Is that clear? All good?
Yes.
Yeah, perfect. So we want to find a measure that goes up when that mean difference goes up, and goes down when the standard deviation increases and the overlap increases. And let's jump right to a real case. Actually, we can actually swap our axis labels now and put real labels in there. So this is the neural interpretation of D prime in neuroscience. This is how we use it. Let's say you put your firing rate on the x-axis. Let's say I'm recording from an IT neuron, and I suspect that's a face neuron. That's a face selective neuron. How do I calculate D prime for that neuron? Neural firing rate is x-axis. Frequency is y-axis. What is frequency? It means that if I show, let's look at the blue curve. I show a non-face stimulus. It drives the cell by whatever amount. That will make 1 point. I show I show 1,000 non-face stimuli. It turns out that most of them drive the cell at the peak of the blue. That's the average background activity of the cell, something like that. And some of them drive it less than that. Some of them drive it more than that. When I show faces, that whole distribution shifts to the right. Now, the average face stimulus is driving the neuron even more. And some of the faces activating it less, some of them more. The question is how, if an ideal observer looks at that neuron, how good that ideal observer can tell if there was a face on the eye, on the retina, or there was a non-face object on the retina. And the way we do it is with this formula. D prime equals to mean of face responses, that's mean of red, minus mean of blue, right? That's the difference between the means. That's what we want. The higher that is, the better, the more the D prime. So if the mean response to face is far higher than mean response to non-face, D prime goes up. And then on the denominator, we basically have the average variance of those two distributions. We take the variance of those two, we take the standard deviation of those two, take an average, and take a root square. So basically the denominator there, the fatter those distributions become, the wider those skirts go, the bigger the denominator becomes, and the lower the D prime will be. And the more the means of them get distance from each other, the higher your D prime gets. Is it clear? Everybody understands that.
I have a question, and this isn't exactly a clarifying question. I'm just wondering for the faces that have a lower neural firing rate response, is there something consistent about those faces and what pictures are being shown between people?
Oh, you mean generally?
Yeah.
About yeah. Well. Honestly, we don't know. Honestly, we don't know really what is it that drives the face cells. We will have a session on them and talk about them in details. But that's what you get in practice. I mean, face cell, even that word I hesitate to use because there is a gray zone, right? There is there's a DPrime. I kind of like to say DPrime more than one, I call it a face cell. DPrime less than one, I don't call it a face cell, but that's totally arbitrary, like where you draw that line. Okay, so we are done. We can pack and go home. That's the interpretation of DPrime in neuroscience. Well, that's the neural interpretation of DPrime in neuroscience. If you want to talk about psychophysics and behavioral results, then it's a different beast, because now if I have a neural recording, I have the distribution of responses to faces and non-faces. I have the whole distribution for both cases. I can do that math that I just showed you. But that math goes out of the window as soon as you switch to a basic psychophysical measurement, because now you are not measuring the whole curve, you are measuring the interaction of your criterion with 2 points on the curve. Basically, you are giving me the task, and what you measure is my performance. Did I say yes to this trial, or did I say no to that trial? You don't have it's a binary distribution. You don't have the actual distribution of the noise and how my choices interact with that. How do you solve that problem? How do you if you have my data with, well, what do you have? There are 4 conditions. You have the stimulus in there, shown the stimulus to me, and I have said yes. You have the stimulus in there, I have said no. You don't have the stimulus there, I have said yes. You don't have the stimulus there, I have said no, right? There, I forgot, like 2 by 2 conditions. So how do I reconstruct the DPrime from that? And that's the rest of our discussion for today, but this is a story time. Because if you want to understand that, you need to understand some basic math concepts before that. The myth of Poincaré, Henri Poincaré, if I'm not slaughtering the French pronunciation of the name, and the baker. So Poincaré was this annoying mathematician, you see his picture to the right, who had this really annoying relationship with the baker of his neighborhood. So he was buying bread, and the standard weight of the bread was 1 kilogram. So he buys bread for a whole year, and he actually weights the breads that he buys. And then after a year, he takes the baker to the court and say, hey, mean weight of your breads are less than 1 kilogram. You are cheating. So the court finds the baker. And now the baker wants to continue cheating, is making money. But now there is this annoying guy who goes measure things and comes in with means and cause trouble. So what's the solution? The baker is like, every time Poincaré shows up, I give him one of the big breads. So basically, when the bakers make their bread, they don't do it with a machine, they do it by hand. So they get a distribution, right? Even though his average is less than 1 kilogram, some breads happen to be bigger and cross that threshold of 1 kilogram. And he's like, every time he comes, I give him one of those, because my other customers are not going to weigh their breads. He is going to do that. So, and he will get an average more than 1, and I'll be fine. A year later, Poincaré comes back and takes him to the court again. And here is the argument. He's like, that was the distribution of the weights that you gave me, the breads that you sold me. They're all above 1. That's suspicious. It's not a Gaussian distribution. It's actually an asymmetric distribution. And look what I do, what I get when I actually fit a Gaussian to that. You have not changed your scale yet, right? So this story I'm telling to just show you, if you have a tail of a distribution, you can reconstruct the rest of it. Actually, a Gaussian function is a 2-dimensional thing. It has only 2 parameters, mean and standard deviation. So you can easily constrain that, and you might not need the whole distribution to infer the D prime. If you make the assumption of normality, you will be fine. Everybody on board?
Yeah, I think that's very interesting, that the fact that you have this prior about the sort of the distribution is allowing you to do all this, and that's
exactly
really...
exactly. And things will go to the dogs when that prior fails, right? When something is not Gaussian, then you're screwed, and you have to do a lot more things. But when you make that assumption, that makes life very, very, very easy, actually. So now let's talk about psychophysics and how do we actually make that we've got like another, we are until 6:30, right? Yeah. So here is how we do the math. So let's say, actually, let's do the math together. That's what I want us to do together now. So let's say that's me. That's me. I have a lax criterion, and you're doing the test on me, right? So for me, my internal rule is that anything below that threshold, I say no to that. That's not a signal. Anything above that, I say yes to that. That's my internal criterion, right? So what will happen to my performance? We want to understand how is this measure, this D prime thingy relates to the old school performance, percent correct, that we all intuitively understand. So there are 4 cases, as we mentioned, right? So let's explore all of them one by one. The first case is when the stimulus belongs to the blue distribution, is a stimulus absent stimulus or target absent stimulus. The grating, the upward grating shows those cases. In those cases, I have said no. Were I right? I was right, because there was no stimulus in there. So I get this score. And if you look at the 2x2 table to the right, the top side shows the signal. Is it present? Is it absent? The side one shows the response. Did I say yes or did I say no? In this case, the signal was absent and I said no. Good job. Correct. It's called correct rejection. Now, there is this case. All of the cases that belong to the red curve, and they happen to be above my threshold. So I say yes to all of them. Are they correct or wrong? Correct or wrong? Someone says that?
Correct.
Correct, right? Yes and yes. Stimulus present, correct. So we call those hits. I made a hit. And the downward grating is showing that. But if that's my rule for saying yes, I'm going to screw up those ones, the orange gratings, right? Because those are the cases that fall above my threshold. I say yes, but they belong to the blue curve. We call these false alarm, right? That's when I false alarm. There was nothing in there, and I said yes. That's a mistake. And then there is this tiny little bit of the tail of the red one that falls below my criterion, and I have these vertical gratings on it, and those are the misses. I missed those. There was a signal there, but it went below my criterion and I missed it.
Arash,
so we've got, yes.
Can we go over the visual basis for each of, or especially for the misses? Are they, for example, caused by the noise canceling out the signal?
Exactly.
Is that correct? Yeah. Okay.
Correct. Yeah. the noise, being it your visual system noise or the actual noise, is bringing it below your threshold, and you don't have any other option than putting a threshold in there.
Okay, and the false alarms are ones that look like they were signals, but there wasn't actually a signal delivered. Just by random chance, it looked like there was a signal there.
Exactly.
Okay.
Exactly. So now look at that table, the table of 4 elements: hit, false alarm, miss, correct, rejection. How many parameters are there in that table? Is it a redundant, back to the previous session, is there information redundancy in that table? Yes, there is. Yes, there is. Hits and misses sum up to 1. False alarms and correct rejections sum up to 1, because my signal is half and half, right? So for across the trial, let's say signal present trials, if you have my hit, you can calculate my miss because I missed the rest of them, right? Look at the curves. If you have part of them, it's a Gaussian curve, you can calculate the rest of it. So basically, all what I need is 2 numbers, hits and false alarms, to calculate the whole thing, or it could be misses and correct rejections, right? If I have any of those numbers, I can calculate the rest of this plot. We will do examples. Let's put numbers on my results. So in this case, I have cut the blue distribution in half, right? So my false alarm rate is going to be 0.5, 50%. Clear? Now, what is my hit rate? My hit rate is pretty high. I'm doing pretty good on the hit rate because I have lowered my criterion and I don't miss them that much. So my hit rate is 0.98. It is possible to show mathematically, and I hate not to do that and outsource it, but we don't have time to do it here. But this is Wikipedia knowledge. You can easily look it up. It is possible to show that if you only have the z-score of hits and z-score of false alarms and look at the delta between them, you basically get your D prime. And in this case, you can, z-score is basically the function that is making the assumption. It's a Gaussian, and when you put part of it, it basically gives you a sense of how far the 2 distributions are. We are not going into the math of that today because we don't have time, but that's a very simple math.
Can you remind me, what is like the max D prime? Like the highest discriminability?
The highest D prime is infinity because these 2 can go as far as they want. And that's a problem with D prime as a measure, because when we get to infinity, it doesn't behave well. And we will talk about the remedy for that too. Like how do we deal with that? So now, yes.
Arash, quick question. This is Shruti. Question about, Rosa just asked about the max. The min would be 0.
Mm-hmm. The min is, you could say 0, or it could be negative infinity, depending
minus
on
infinity.
Yeah. If you release, like leave the parameters really free, it go from minus infinity to plus infinity.
Is the prime by define is not always positive? It's not absolute value of that distance?
Exactly. That's what we normally do. That's why the minimum becomes 0.
Also, Arash, so if you, I see if you got the 0.5 absent, this is Malcolm, by the way, you have the 0.5 absent, and then in order to get that 0.98, first you would have to assume that they're both normal distributions, right? And then you would also have to know the D prime, right? You would have to know how far apart they are.
Exactly. You know where the rabbit goes to the hat? When you z-score it, basically, because z-scoring means that you are making the assumption of normality on that thing, right? And that's your Achilles heel. If the thing is not normal, the whole plan falls. But if it is normal, z-score fills the rest of the distribution for you. basically. That's where the assumption gets in.
Arash, and it's also assuming that it's the same noise, no? So that it's kind of the same noise distribution for both cases.
Exactly. It is making that assumption too. Yeah. So although there are variants of it that you can change that assumption on it, but we are not getting into that. So now let's compare two cases. Let's compare two cases. Let's say the person on the top is me, and I am kind of I'm a lax guy. I kind of like to say more yeses. I'm not careful with my yeses that much, but that's my discriminability. I have normal vision, and the stimulus imposes that DPrime to me. The bottom person, let's say that's Rosa, is more balanced than me, and it has a balance of yes and no's, and puts the criterion right at the center. Let's say if that helps Rosa with the DPrime, let's calculate the DPrime. So now, if you put the criterion at the center, now you have your hit rate drops to 85% correct in this case, because we have shifted the criterion, but by false alarm rates decreases, her false alarm rate decreases, right? So now her hit rate has gone from 0.98 to 0.85 drop, but her false alarm rate is also dropping from 0.5 to 0.15. And if you do z-score of that minus z-score of this, you will get 2, again, the same number. So Rosa and I have the same discriminability. We see the differences the same way, but we have different choice biases, right? The DPrime has managed to distill our discriminability out of our choice biases. Now, there is more fun things you can do. You can do more math game and actually calculate the criterion. The position of the criterion is actually z of hit plus z of false alarms, and divided by 2. So you can actually put a number on my C and put a number on Rosa's C, and see that Rosa is balanced. Her C is 0, but my C is off, is negative, or it could be positive if I am off to the positive side, right? Okay, interesting stuff. So that might tell about our choice biases and stuff like that. But let's stop here and ask everybody, are you with me? Has everybody understood this? Like, if I go ahead randomly and pick someone and ask a question, are you sure that you can answer? Yes? I want to hear. I want to see hands.
Actually, I have a quick question. I kind of lagged out. Hi, sorry, my name's Alex.
Alex.
For the choice bias part, you said it could be negative or positive. How do you discern that again?
Oh, that's the criterion. You see that vertical line? That's my criterion. Mathematically, you can calculate that. Again, I'm not going through the math because that will take more time and we are running out of time, but that's available on Wikipedia. You can easily look it up, how to calculate that. The formula is what I showed over there. Basically, the position of C on the x-axis is calculated like that. So 0 is where the two distributions are symmetric. When you go negative, you are sort of becoming more lax. When you go positive, you become more strict of an observer.
Okay. Got it. Thank you.
Thank you. So now that everybody is on board, I have a task for you. Can you tell me what is my percent correct and what is Rosa's percent correct on these distributions? Like the traditional percent correct. Correct divided by all. How many of those did I get correct? Like if you were rewarding me for correct choices, how many rewards would have collected? And how many rewards would Rosa collect? Somebody should tell us, how do we do that?
You're going to have rewarded on whatever you said as a hit and also as the correct rejections. also Rosa have the correct rejection. So you will have a 98 and 0.5, which gonna be 145. Rosa gonna have 0.85, 0.85, which is more than you.
Beautiful. So let's write it down. So what are the correct choices? The diagonal, the green diagonal is the correct choices, right? So my hits and correct rejections are my correct choices, divided by all of them, which is 2. The sum of all of them is 2 in this case. So hit plus correct rejection divided by 2, and you multiply it by 100 to turn it into a percentage. So I got it with my criterion, I got 74% correct in this case with DPrime 2. How many did Rosa get? Shoot, Rosa got 85% correct. What the hell? So this is what I mean by percent correct being contaminated by the choice bias, right? So basically Rosa has managed to distribute her responses in a way that she got more corrects out of it, and I got less corrects out of it. But if you take out the effect of our biases, we both have the same vision. We both have the same discriminability. That's the concept of DPrime. And now, before we end, there is one more beast for you guys to slay, and then I will feel happy about today, and that will be ROC, Receiver Operating Characteristics Curve. That's also a very common concept that's used a lot in neuroscience and psychology, and it's kind of bread and butter. That's basic literacy. So let's talk about that. You remember I mentioned that the table with four numbers is only actually 2-dimensional, right? If you have hits and false alarms, you can calculate the other 2. So it's a redundant table. So basically what we need to describe an observer is those 2 numbers. And why do we call it receiver operating characteristics? This is one of those terms that kind of feels weird today because it is old. It's a term from 40s. It meant that the radar operator, who is the receiver of the radar signal, what are the operating characteristics of that person? Operating characteristics means that how lax is that person or how strict is that person, basically. Okay, so let's do it. Let's take my results and see, okay, I got 0.98 hits and I got 0.5 false alarms, right? I can put that on the plot to the right. That point is me, right? That's like halfway through the false alarm axis and quite high on the hit rate axis. That's what I got. Let's put Rosa on that table, on that coordinate. Rosa is sitting there. So Rosa is 85%. Her hit rate is a little lower than me, but her false alarm rate is much, much lower than me as well. So what? Here is so what. This is the fun part. Now I can actually exhaust all possibilities. I can imagine that is the visibility of the signal for all of us, but we are a group of people with all different criteria. Some of us are very lax, some of us are very strict. So let's calculate that for everybody. And what happens is that those dots land on a curved line, all of them. So this line is called the ROC curve. The ROC curve is basically the sum of all points that have the same DPrime. We all have the same DPrime. We see the world like each other, the same. We are the same, but we have different criteria. So on the ROC curve, if you are the most balanced subject in the world, you are basically where Rosa is sitting. You are in the middle of the bow. If you are very lax, like the top case, like me, what happens is that you're saying a lot of yes, right? So your false alarm rate increases. So the more lax you are, the more to the right you move on that bow. The more strict you are, the more to the bottom you move on that bow. But basically everybody with all of their thresholds fall on that line, and everybody on that line have the same D prime. So what happens if you have higher D prime? So basically, let's get rid of the half of that plot because we never use it. What happens is that as your D prime increases, that curve, if we do the math and we do the simulation I just showed you, that curve will bow more and more and more the higher your D prime gets. So basically, if you are totally random, totally crap, you will be the unity line. You will be that 45-degree line, the solid line that slashes the square. That's no signal. As you start seeing signal, as you start discriminating, your curve bows. So basically, if you make it to the points 1 and 0, that's the ideal case, right? All hits, 0 false alarms. That's 100% correct, right? So the higher your D prime gets, the more bowed you get. So let's say the cat-eyed squadron of the British Army are the very bowed one. The low vision dudes around the poker table are sort of less than that, and normal people like us are in the middle of that. Everybody understood this?
Yes.
Thanks. Now there is this concept of, so basically what I showed you is the concept of iso D prime lines, right? On each one of those bows, the D prime remains the same. And if you hop onto a higher D prime line, you have to hop on a line that is more curved, right? So now you can measure the area under that line. The area under ROC curve, it is called. Or in some measures, they call it A prime. I welcome you to look up A prime on Wikipedia. That's also one of those formulas that you kind of play around with your hits and false alarms, and you get an A prime. That's another measure, highly correlated with D prime. It's just the area under that curve. It has one advantage over D prime, and that is it has an upper bound. It doesn't go to infinity. So basically, if you are dealing with a case that your D prime is sort of getting into infinity a lot, then D prime might not be a good measure for you, but you could use A prime instead. The last point, the last mathematical point that I want to communicate is actually something, it was an epiphany that I gained in grad school. One day I got really mad that, oh, I don't understand, how does D prime work with the percent correct, and every time I have to run a formula to do that, it's not intuitive. I can't see it in my head. Can I make that intuitive? And this is what I came up with. The math is in a PDF that I composed back then, and it's on my homepage. You're more than welcome to dig in. But this is the intuition. This is the intuition that helps the understanding. So let's say there is my curves, right? And that's Rosa's curve. And we land on those two spots on the ROC curve, right? We are both on the same ROC curve. We have both the same D prime. What are our performances? Percent correct? Well, she's 85. I am 74. But what about other people? Other people on that line, what about them? Like, how would their performance change? Like, if I go now to a new point on that curve, how can I estimate percent correct? I want to understand, how does percent correct interact with D prime, right? So if you do the math, so one way to deal with it, that was my intuition, was that let's take all the spots that have 85% correct and connect them in a line, and take all the spots that have 74% performance correct, not D prime, and connect them in a line and make iso performance lines. This is what happens. So basically, what you see is that the other people who have 84% performance, 85% performance like Rosa, they happen to be on other D prime curves. And if you solve it for the general case, what you get is this beautiful plot, which is very intuitive and important. So the red lines are iso performance lines. On the ROC plot, it's a linear function, basically. Every performance which is the same falls on a solid line. Every D prime that is the same falls on a bowed line. So now you can see what happens to your performance when your criterion changes, right? So let's do it together. Let's take that most bowed curve, the most bowed curved, right? That's the cat-eyed squadron, right? Those people, they see really great, but some of them are less biased. They are the ones who sit at the belly of the bow. Those ones touch the farthest iso performance line. They make the highest performance. As you move away from the center of the bow, you're going to cross other iso performance lines. So your performance is basically dropping. Remember, the iso performance line, which is the black line, which is the black diameter of our square, that is 50-50. That's 50%. That's when you're chance level, right? No performance, no D prime. The iso performance line at the very corner, very top corner, is 1. That's performance 1, 100% correct. And D prime infinity, A prime will be half, basically. Maximum of A prime is 0.5, right? Because it's half of that circle. So you get to the maximum A prime, maximum D prime, performance of 1, right? Now, even if you are on a highly bowed curve that will make it to, let's say, 90% performance line, if you bias your choices, if you become lax or strict, you are moving away from the belly of the bow, so your performance is falling. Your performance is falling. If you actually manage to get to the 0.00 or 0.11, your performance is gone. Those points are awkward points, right? If you are on 0-0, you don't have any hits, you don't have any false alarms. There's nothing to calculate there. And if you're on 1 and 1, it's kind of it's a similar situation because you could be on either. Mm-hmm.
At 1 and 1, aren't you at 50%? Because you're hitting 100%, but you're also failing to correctly reject.
At 1 and exactly. At 1 and 1 and at 0 and 0, both of them you're at 50%. Because remember, the 50% iso performance line is the diameter of this thing, right? So you're at 50%, but that's an interesting case of limit, mathematical limit, because if you move an epsilon away from that and you happen to be on a highly bowed curve, you're good to go. You all of a sudden you have a high D prime, right? So those are peculiar points, but yeah, officially when you land there, your performance goes, your D prime goes to 0, your performance goes to the chance, right? So basically, as your D prime increases, your performance increases, but your performance follows those lines and D prime follows those bows. That's the intuitive take-home message, is that if you don't have any choice biases, meaning that you're sitting in the middle of the ROC curve, you have the most performance, the highest performance. And the more biases are introduced into your function, the more your performance drops. You go into the lower lines. And everybody with me on that?
Yeah, I think it's a really very kind of intuitive, graphical way of representing this. And I was wondering, I mean, I find that interesting, but people can kind of change subject if I'm getting stuck here. But I find it very interesting to think about the limit points of this diagonal, because in the end, you're trying to estimate a distribution. So you're always like sort of thinking like at the level of the population here. So in reality, you might get a kind of to the corners here, but you can't. In infinity,
Exactly.
that cannot happen actually, because eventually there will be something of the noise that will actually break that. So these points, those points are possible in the sample, impossible in the population. So that's sort of
exactly. Cool. I agree. Yeah, exactly. It also helps you visualize, like when you think about DPrime and percent correct in your mind, it makes it much faster, basically, to see the rules that govern that. So
can I say
if
something?
It is, Reza.
I mean, it's off the track of this, but when you talk about point, any point in this curve is impossible, because mathematically, statistically, any point of being on any point is impossible. You're on those lines.
Yes, but they're impossible in different ways.
Yeah.
That's right. That was the perfect answer. Yeah. So, I want to say one more thing and then finish. This whole thing that we talked about, is when you don't have a two alternative forced choice design. And there is a very common misunderstanding of two alternative forced choice design, or 2AFC. I've seen this mistake in papers, in like high rank papers, and I want to pull out my remaining few hairs when I see that. And so the idea is that when you show me one stimulus and offer me two answers, two choices, say yes or no, was it there or wasn't it there? That is not a two alternative forced choice. That is what we discussed so far, and that is subject to choice biases. And we want to do that in many cases because we want to measure the choice bias. Choice biases are important. They are very informative if you are interested in decision making or many things. But if you want to get rid of your choice biases off the bat and don't bother with DPrime and any of these things, you can have a two alternative forced choice design. And that is, instead of showing me one stimulus and telling me yes or no, show me two stimuli and tell me which one was that, which one contained the signal. So basically, in 100% of the cases, there is a signal. I just have to say left or right. So basically, I am forced to choose that. And you randomize your position of your left or right. So now, if all the time I say right, 50% of the case I would say detect, 50% I wouldn't detect. So I would not be able to shift anything on that function. I just wanted to briefly mention that there is a design way to get rid of choice biases, but you don't want to do that because the DPrime and choice biases are very useful and they can be very informative. And we end today's session
Arash,
by yes.
Can you explain it again? I didn't understand.
This one? Yeah. So this one I'm hoping to explain more when we get into this method session. But the idea is that if you show me one stimulus, right, and tell me yes or no, I can choose my yes and no distributions in a way to reveal my biases. Like, let's say I am a guy who is very lax, right? So let's take the extreme case. All the time I say yes, right? So what happens if I do that? If I press one button all the time, right? And that's the yes button. So my performance on target present trials will be 100%. I won't miss anything. But my performance on target absent trials will be 0, right? Now, in a two alternative forced choice design, you show me two stimuli. It could be left and right, or it could be back to back, right? First and second. One of them always contain the signal. You just randomize the position of them in time or in space, right? Because it is random, if I am stuck to one choice, if I'm like, I'm going to press this button all the time, I'm going to say yes. Well, there's no yes anymore to say. I got to say left or right. And if I say left all the time, you are swapping left for me. You are sometimes showing it to the left, sometimes showing it to the right. So if I am the extreme case and only press the left button, my performance for signal present cases will be 50%, because only 50% of them occurred on the left. And my performance on the signal absent trials will be 50%, right? So my psychometric curve.
Yeah, but how could you make psychometric function? So you only have noise in one side and signal on the other side, and the x-axis is the.
Yeah, so you would vary the amount of signal on your signal, right? And so basically you still have percent correct. Your vertical axis will be percent correct, and the x-axis will be signal. But what happens is that your zero signal case is forced to be at 50-50. Because there is no way you could bias that, right? Even if you press one button all the time, when the signal goes down, you will cross the 50-50 point. At zero, you are at 50, right? But on the case to the left, in the case that you show me only one image, and I should say yes or no, then at zero, I might be 100%, or I might be 0%, depending on my bias. And that's the difference, basically. 2AFC forces you to cross the point of neutrality and takes away your choice biases, because there is no choice bias. It's impossible. You are randomizing the choice, basically. So, yep.
I guess, would this example also be a two alternative forced choice design if you had a single stimuli, but like if it was like a Bohr patch and you had the directionality either pointing left or right?
Fair enough, exactly.
Because it's the same thing, you're forcing that.
Exactly.
Okay, I understand.
Exactly. It would be the same. It could be that it's not necessarily signal present, signal absent. It could be signal A, signal B, right? Your task is to tell me if the Gabor is tilted to the left or to the right. Yeah, and you have Gabors in both cases, but you randomize the orientation of them. So now if I say left all the time, I will remain 50% because you're swapping that on me.
That makes sense.
Yeah. So we finish today by making an honorable mention of Stanislav Petrov. He's not a scientist. He's actually, he was not an important person by any measure or definition, but he was the one who saved the world. And I know the word that title, someone saving the world, is super meaningless and stupid. But I guess in his case, it's as close as it gets to saving the world by one person. In 1983, at the peak of the Cold War, United States and Soviet Union had their nuclear missile arsenal pointing at each other. And it was at that time, the idea of political balance was mutual assured destruction. It means that I can destroy you, but you can destroy me too. So we have these guns pointed at each other's heads and none of us will shoot. That was the idea. But if one person shoots, what will happen? That was the nightmare of people growing up in those times, including myself. And so basically, what if both cases want to do it? What if one side do it, right? Then you got 20 minutes, only 20 minutes until the nuclear missiles of the enemy hit you and destroy your civilization. In that 20 minutes, what you would do, you would shoot your own missiles to them. That was mutual assured destruction, right? Destruction of the world. So Petrov in 1983 was the head officer in charge of monitoring Soviet radars, looking at tracking the potential nuclear launch by the Americans. And they detected a launch. So from Petrov's point of view, lots of ballistic, intercontinental ballistic nuclear missiles are coming his way, Soviet way. And his job was to press the alarm button, and the whole chain of basically making the counterattack would go off. And he decided not to report it. And for 20 minutes, he lived in hell, right? Because if there are actually missiles coming, oh my God, like in 23 minutes, I will lose my job, but that's the okay case because everybody will lose their jobs. But if in 23 minutes they don't come, that's the irony of it. I will lose my job because I failed to report the case. And he decided to do that. Why he decided to do that, I don't know. There were people at the time who were thinking even about this. This is crazy, like when you think about humanity pushed to the extreme. There were people who had this philosophy of, if your opponent shoots their missiles, the humane thing is not to respond, because at least half of humanity makes it out of the mess. Although now we know that 17 of those explosions were enough to destroy the whole planet. The ecosystem would crash, and we would all be having this class in a forest writing on rocks with chalk. Actually, that could have been more fun. But I decided to give, from our course, this administration, we give the 00 Medal of Honor to Stanislav Petrov, and that is for being on 0.00 on the ROC curve. His D prime is 0, but his D prime was not 0. He actually saw it. So I finish it here, and thank you, and let's chat if there are any questions left.
I have a question.
Simon.
So, I want to talk about the 0.00, and I'm curious if there's any way we can find the intuition of it hopping from D prime 0 to a high D prime on the plot of signal and signal plus noise. Can we get that out of it?
That's a good idea. I don't know where it goes. Let's try it. Let's try it.
Yeah, that's what I'm hoping.
Yeah. Let's see. Let's go there.
Because it doesn't make any sense. It doesn't, like, naturally, it doesn't make any sense.
Yeah. I don't know,
it's
actually.
A continuous line moving across. Yeah.
I know. Yeah, I don't know the answer to your question, actually. Let's see. Let's find out. Where do I go?
What's the question?
So the question is, it's if you follow the ROC curve at D prime 0, 0, or sorry, at hit 0, false alarm 0, you have D prime 0. And then you follow your ISO D prime line 1 epsilon up, like 0.001 up, and suddenly you're at a very high D prime. How can that be possible if we look on one of these charts?
Yeah. Do you see my screen?
Yes.
Yeah. Okay. So let's talk through it. I don't know where it goes. This is fun. So let's say we are at 0.00, right? It means that our false alarm rate is 0 and our hit rate is 0. So that means that we have shifted the criterion all the way to the right. So I don't say yes under no circumstance. Everything is a no, right? So, okay, now I understand. Okay, that's cute. So when you are there, so what determines, how do you sniff what is your D prime? As you go away from the center, you have that little tail to work with, right? You have this little tail of the Gaussian. You have to reconstruct the rest of it with that. So as you go far and far and far to the right, that tail becomes smaller and smaller and smaller. It kind of falls down on the other one, right? That's where estimation of where that tail is becomes very noisy, right? So basically, when you go to all the way to the right, you can't tell where you are because you don't see the Gaussian anymore. It has flattened. But when you travel back, you just move your criterion a little back, then you see if the tail is taking off like that, or is taking off like that, or is like that. So that slope will tell you which D prime line are you on. But when you push all the way to the flat part of the tail, you wouldn't be able to discern that. It will become flat, right?
Yeah.
Yeah, I think this is it's an interesting point, and I think it's maybe also the right moment to kind of remind that this, in the end, the key concept is of signal to noise. I mean, this is really what is underlying this whole thing. And it shows up in different ways. In the beginning of the class, it showed up in the distance of the means of the distributions. That was
divided by.
That's the signal.
By their.
Exactly, divided by the variance of the noise. And then you assume some stuff about this, and it's the same, and you estimate it, and you have a signal to noise ratio in the end.
Yeah, exactly.
And now it pops in an unexpected way due to your question, which is sort of cool to think about, that in the end, there's also an SNR in the estimate of these things, depending on what your criteria is.
Yes.
And that's also really sort of cool to think about. I've never thought about it, but I will definitely be thinking about it tonight.
Fernando, is that let's think about that actually. I should think about that too, because is SNR, if SNR is a little different from D prime, but if in this case, if we take SNR as D prime, then it's funny, it is related and it is not related. It depends on how you define it. Because then you move your criterion, your D prime doesn't change. By that definition, your SNR is not changing.
Yeah, because it's in the end, it's the additional layers. In the end, it's SNR. It's like a model of SNR plus decision.
Yeah.
So you're somehow plugging in a mathematical description of the decision process on top of that.
That's right, and you want to distill that out.
You want to estimate the underlying SNR.
Exactly, that's what you want. Exactly.
So, and then you find kind of tricks to kind of get there. Yeah,
I agree. I agree.
So if you're relating this to SNR, and so would that mean that your criteria would kind of be like a threshold almost, basically just like what?
It is a threshold.
Yeah. So like if you're relating that to like MRI almost, it would be like, okay, what are we thresholding this voxel at? And then, okay.
Yeah. Totally.
Totally. Exactly. Yeah, exactly. With one glitch, that what you are thresholding on is not necessarily luminance. It could be a higher level construct of your signal, right? So you can pre-process your signal, warp it, turn it into something else, and look at the signal to noise ratio or detectability of that parameter. That's sort of the general case.
I also had a question about the ROC curve. So when you have the performance lines, that would never change, right, on every ROC curve. But like the what are the curves called?
The ROC curves.
Okay, yeah. But the curves would change depending on the task or like what's happening, right? So like
exactly.
So like if it's a really hard task, you wouldn't have anything going up to one performance. You would have
exactly. If it is a very hard task, it would flatten basically.
Right.
It would be a very not pooled bow. If it's an easy task, it will be a pooled bow, right? Okay. It will be bent, more bent.
Okay.
Can you give an example of an easy and a hard task in that circumstance?
Yeah, easy and hard task is basically our spot is very bright or our spot is not bright enough, right? So if the spot is not bright enough, what is happening is that the two curves get into each other, overlap more, because we are adding less to the noise, right? But if our spot is very bright, we are adding a lot to the noise. So we are shifting it away and increasing the D prime. And of course, I am making all these examples with the spot and the physical stimulus, assuming that the visual apparatus of everybody who is looking at that is the same, but that's not the case, right? So in practice, what we use this for is to actually discern the differences between different people. And so there could be, if you want to measure vision, not everybody's vision is the same, low level, high level, different ones. And that's how you measure it. So it's mostly referring to the internal noise of the system. In practice, that's what we pull out of it, and we use it for. So can everybody here tell confidently that they understand D prime and A prime and the notion of choice biases? Yeah, Excellent, excellent. So okay, good. Because once you understand something deeply, then you can be creative about that. You can be thinking about other variants of that. I hate practicing science in a religious way, and which is kind of looking at the stats book as if this is the holy book, and whatever it says, you just follow, put the numbers in there. And to be able to break that, you have to have a grasp of the basic concepts. And I'm hoping this was communicated for signal detection. And thank you very much for bearing with me. This was a particularly long session. Thank you.